All right, so what do you think happens when you smash tiny particles together at, basically the speed of light? You'd probably guess you get a nice, clean, simple result. But this is the quantum world we're talking about, and it is anything but simple. Today we're going to dive into a really cool puzzle, the strange case of the W boson and why it rarely ever travels alone.
So let's start with what seems like a super simple question. If you go through all the trouble of creating a new particle, say a W boson, which is one of the fundamental carriers of the weak force, shouldn't it just pop into existence by itself? I mean, in our everyday world, that just makes sense. But the quantum realm? It plays by a completely different rulebook. And as we're about to find out, alone is almost never the answer. And this really gets us to the main event here. When physicists smash particles together to create W bosons, they see something a little weird. The W boson doesn't just show up solo. It almost always brings a friend to the party, a high-energy spray of other particles that our detectors see as a jet. So here's the play-by-play. You've got two particles, let's say a couple of quarks, the things that make up protons. They collide to create our W boson. But at the same time, another particle often gets kicked out of the collision. It could be a different quark or maybe a gluon, the particle that literally glues matter together. Now, because of conservation of momentum, the new W boson has to recoil from this extra particle, kind of like how a cannon jerks backward when it fires a cannonball. And that energetic particle that got kicked out, it immediately breaks apart into a whole shower of other particles. And that's the jet we actually see.
Okay, this is where our normal, everyday logic just completely falls apart. Our brains want to ask a really simple, logical question. Okay, so which one of the original particles spat out that extra gluon? But in the quantum world, that's a question you're just not allowed to ask. It's fundamentally meaningless.
And this is the absolute key to understanding all of this. Trying to figure out which incoming quark was the one that emitted the gluon, it's like trying to apply street directions to a dream. It just doesn't work that way. See, in the quantum world, reality isn't one specific thing happening. It's this fuzzy, weird, probabilistic combination of all the possibilities happening at once, and they all interfere with each other. This whole thing should sound really familiar. It's almost a perfect echo of the famous double-slit experiment, right? Remember that? You shoot one single electron at a barrier with two slits. It acts like a wave, somehow goes through both slits at once, and creates this wavy interference pattern on the other side. But the second you try to peek and ask, hey, which slit did it actually go through? Poof, the wave behavior is gone. It acts like a boring old particle. Asking which quark coughed up the gluon, it's the exact same kind of forbidden question. It just doesn't compute in the quantum world.
But look, even though we can't ask which one, that doesn't mean we're just flying blind. Physicists are clever, and they figured out a way to handle the chaos. It turns out you can sort these messy interactions into a few different categories that don't interfere with each other. And because they don't interfere, you can actually study them and calculate them separately.
So it basically boils down to three main ways this can happen. Scenario 1, a quark smacks into an antiquark. Scenario 2, a gluon hits a quark. And Scenario 3, a gluon hits an antiquark. Now, here's the really important part. Because the starting lineup of particles is different in each case, we can treat them as totally independent events. We can figure out the probability for each one without them getting all tangled up together, and then we just add up the results to get a total prediction.
So how in the world do physicists predict how often each of these things is going to happen? Well, this is where they put away the abstract ideas and pull out the big guns, the super precise language of mathematics. They use what you can think of as a recipe to describe these interactions with stunning accuracy. Okay, don't get scared by the equation on screen. Seriously, you don't need to solve it. The important thing is just to know what it is. This is something called a quantum amplitude. Think of it like a recipe. You plug in the ingredients, the energy and momentum of the particles, and out comes a number. Then you square that number and bam, you've got the probability of that exact interaction actually happening. This is really the mathematical engine that drives all of quantum mechanics.
But there's a catch. Like any complex recipe, this one has a potential flaw. If you look at the terms on the bottom part of the fraction, the denominator, you'll notice they're tied to the energy and momentum of the particles. So, what happens if one of those terms gets really, really close to zero?
And that single question leads us to the coolest, most mind-bending part of this whole story. Because whenever the math in a physics theory seems to break, it's usually pointing to some deeper truth about how the universe works. And in this case, when that denominator gets close to zero, our beautiful recipe starts to predict something completely impossible. It predicts infinity.
This specific problem has a name. It's called an infrared divergence. And this isn't just some random math mistake. It's a deep feature of how these theories work. It pops up in two very specific situations. First, when the gluon that gets emitted is soft, which is physicist speak for having almost zero energy. Or second, when it's collinear, meaning it flies out in the exact same direction as another particle. In either of those cases, a term in our mathematical recipe hits zero, and the probability we calculate just explodes to infinity.
So what does it actually mean when your best, most tested theory of reality spits out an answer like infinity? It doesn't mean the universe has a bug. It means our understanding has a blind spot. An infinity like this is a clue. It's a giant flashing neon sign pointing us toward a deeper, more elegant truth about how nature really works. A truth that's just waiting for us to figure it out. So what do you think that truth could possibly be?